looking at related rates. Related rates is an application of derivatives where we consider two or more quantities that are related in some way. When we look at the different quantities, we then figure out what happens to the rate at which one quantity is changing with respect to when some other quantity is changing. So it's a related rate because we're looking at a rate of change for different elements, and we're looking at how these different rates of change compare. So let's work through a few examples so we can see what we are working with related rates. So the first one here, assume that x and y are functions of t. So those are our two quantities, x and y, and they are related as some function of t. So everything that we're doing, we have it with respect to t. If y equals x to the third plus 2x and dx dt, so that is the derivative of x with respect to time, equals 5. Find dy dt when x is 2. So dy dt, that means the derivative of y with respect to t. And we're looking at x being 2. So we have a lot of information here. We're going to need to use our implicit differentiation strategy because we are differentiating multiple variables with respect to a variable. So we're differentiating x and y, and we're differentiating with respect to t. So first of all, let's just write down what we have, and then we'll work it through one piece at a time. So we start with our given equation, which is y equals x to the third plus 2x. Now for this one, we have our dx dt and we have dy dt. So that means when we take our derivative, instead of doing y prime like we would have done for implicit differentiation, we'll use our dx dt and our dy dt notation. I'll show you what I mean. So the derivative of y, well, that would be the derivative of y with respect to time. So dy dt equals x to the third. Bring down your power, subtract 1. That's our normal derivative. But we have to do this with respect to time. Well, we don't have a time here, so we're going to do our derivative with respect to time. So it'll look like 3x squared dx dt plus. And then we have the derivative of 2x. Well, the derivative of 2x would be 2, but we also have to note that we're taking this derivative with respect to time. So 2 dx dt. You can also kind of think of it as a chain rule. We brought down our power, we subtracted 1, and then we have to take the derivative of the x. Same thing here. It would have been 2x to the 0 power, and then take the derivative of the x. 0 power makes it 1, so it canceled out. So now we have our derivative figured out. We have some information that we've been given. We're still trying to plug everything in, so let's review what we have. We know that dx dt is 5. We're trying to find dy dt. So let's just leave that as dy by dt. And we're told that x is 2. Okay, let's fill everything in. We have 3. X is 2, so 2 to the second. Dx dt is 5. So we'll replace our dx dt with 5. Plus, we're given a 2 right here. And dx dt is 5. So simplify it down. 2 squared is 4. 4 times 3 is 12. Times 5 is 60. 2 times 5 is 10. So it looks like we get 70, and that would be the value of our dy dt. So now we've completed our derivative with respect to time for our equation in x and y. Let's try again. Number 2. Assume that x and y are positive functions of, and then here's our equation, x squared plus y squared equals 25. And dx dt equals 6. Dy dt equals 6. Find dx dt when y is 4. So let's start this the same way. Let's write down our original equation. X squared plus y squared is equal to 25. Now we need to take our derivative. Bring down the power, so that would be 2x. And then just like before, think of it as our chain rule. Derivative of x, dx dt. And then bring down our power to y, subtract 1 would be 1. And then remember, think of it as our implicit with our chain rule, dy dt. Be careful, don't forget the derivative of 25, that's a constant, so that's just 0. All right, let's put it all back in. Here we go. So we have 2. We don't have an x value. Well, let's just skip it for now and we'll figure out what to do later. Dx dt, that's what we're trying to solve for. So there's our dx dt. We have 2 from right here. We're told y is 4 and dy dt is 6. So we're almost there. We've almost got it figured out, but we have to be able to fill in this blank right here. So we need to figure out what x is. Well, fortunately, we have an equation. We know that x squared plus y squared equals 25. And we were told that y is 4. So x squared plus 4 squared equals 25. And we can use this to solve down to find our x value. So we get x squared plus 16 equals 25. Subtract 16 from both sides, so x squared equals 9, which means if we take the square root, we get positive or negative 3. But notice, it says right here that x and y are positive functions of t. So because of that, we know that x has to equal 3. So that means we can put our 3 right here, and now we can finish solving. So no, we weren't directly given all of the information, but what we were given was enough information to be able to solve. We have y equals 4. We can plug that back into our equation, and we have x equals 3. So 2 times 3 is 6, dx dt, plus 2 times 4 is 8, times 6 is 48, equals 0. So if we finish that off, we need to continue solving for dx dt. So we're going to keep working this down so we can solve. So if we keep solving, move our 48, so we'll have 6 dx dt. Oops, let's move this over so we have a little bit more space. There we go. Now we have a little bit more room to write. Move it over, we get negative 48. Divide both sides by 6. Looks like we get negative 8. Let's try number 3. Number 3, suppose that x, y, and z, so we have 3 different variables this time, x, y, and z, are positive. So that was that note from last time. Functions of t. If z equals x squared plus y squared, if z squared equals x squared plus y squared, dx dt equals 2, and dy dt equals 3. Find dz dt when x is 5 and y is 12. We have a lot of information there. Let's start with our equation and then we'll work it down. So our equation says z squared equals x squared plus y squared. So that's our equation from right here. So let's take our derivative. Everything is with respect to time. So z squared, bring down your power, subtract 1, dz dt. Just like our implicit differentiation. 2x, bring down your power. So it was x squared, the derivative is 2x. And then we have dx dt. And we have y squared, so bring down your power, 2y, and dy dt. So we have all of our derivatives with our chain rule attached, with our derivative with respect to time. So let's fill in what we know. Z. Do we have a Z? We don't have a Z. So let's just skip it. We'll move on. 2, that'll be our Z. dz dt is what we're trying to find. So that stays dz dt. 2x we're told is 5. Do we have dx dt? We do. Right there, it's 2. Plus 2, do we have y? Yep, 12. And dy dt is 3. So we have some pieces and we don't have others. Let's see if we can figure out z. Well, we know that z squared equals x squared plus y squared. So z squared equals 5 squared plus 12 squared. Well, that means that z squared equals 25 plus 144. So z squared equals 169. So that means that z would be positive or negative 13. But it says positive function, so that means that z is going to be positive 13. So then we can put our 13 back over here. So now let's simplify it down. So we have 26 dz dt is equal to 5 times 2 is 10 times 2 is 20. 12 times 2 is 24 times 3 is 72. And then we can add these together. So 26 dz dt equals 92. So it looks like dz dt, once we divide, is going to be, simplify it down. So we'll be able to divide both by 2. So 92 over 26, which will simplify down to 46 over 13. There we go.